the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students, and only linear algebra students, who are going through matrix arithmetic right now. You probably have just learned about the inverse of a matrix, specifically if you're following my video sequence, the inverse of a 2x2 matrix. And then we played around with some stuff in there. There are some very important theorems from that video, so I highly recommend that you watch it if you have not already. This video will focus on a very small area of linear algebra that ends up growing to be a massively important piece, but it seems very simple at first. Even though it seems simple, you should have already realized linear algebra is laid out upon the framework of very simple ideas, and they become complex very quickly. This video will be somewhat long. We'll start with this idea of what an elementary matrix is. We could have defined this way long ago, but there was no need to. We didn't need them until now. So let's define an elementary matrix. Well, an elementary matrix is obtained by performing a single elementary row operation on an identity matrix. I say an identity matrix because obviously there are an infinite number of identity matrices. There's a 2x2, a 3x3, a 4x4, a 5x5, and so on and so forth. For example, imagine you had this identity matrix. Let's just make it a 3x3. It's not that big of a deal. If I wanted to take, let's say, 7 times row 2 and add it to row 3, we get this guy right here. And there's really not much to be said about that. That is called an elementary matrix, and we use the notation E subscript whatever we want to. For example, in this case, I might call this E sub 1 because I might apply another elementary matrix a little bit later on in a problem, for example. One thing you need to note here is that all elementary matrices are very simple looking. They're just a very slightly modified identity matrix. This one specifically just took 7 times the second row and added it to the third row to become the third row. But something fascinating happens when you deal with elementary matrices like this. And to showcase that, let's just do an example. Let's write a 3x3 elementary matrix for multiplying row 2 by 8. There's our original identity matrix. We're going to multiply row 2 by 8. I'll call that E sub 1 just for this problem. Now let's write a different elementary matrix that will swap rows 2 and 3. There's my identity matrix. Now if I swap rows 2 and 3, and I'll call that identity, or that elementary matrix, to E sub 2. Finally, let's write another elementary matrix that will add -5 times row 2 to row 1. So I start with the identity matrix. I'm going to multiply row 2 by a -5, and then I will add that to row 1. And I'll call that E sub 3. So what's fascinating about these elementary matrices is that they perform the same operations you performed on them on any matrix you multiply them against, as long as that matrix is the proper size. For example, oh, by the way, that matrix multiplication has to be from the left. For example, if I said, oh, I have this matrix A, and the matrix is just make it 1, 1, 1, -2, 1, 0, and 0, 3, 1, something like that. It doesn't really matter. It's not that big of a deal. Main thing I want is for right now to have it be 3x3. If I multiply it by E2, remember what E2 did to the identity matrix? It swapped rows 2 and 3. So if I take a look at E2 times A, and it has to be left multiplication by E sub 2 by the elementary matrix. But if I do that, you'll see the result is this matrix right here. And I did actually go through and make sure I was doing the mathematics, but really in the end, it doesn't look like I did it, but I swear I did do the mathematics. But look what it did. It just swapped rows 2 and 3. So it turns out whatever application we put on the identity matrix, so whatever elementary row operation we do to the identity matrix, if we apply that resulting matrix to any properly sized matrix through left side multiplication, that product will result in the same elementary row operation being done on that matrix A. You can test this out if you want using E1 and E3. on that matrix A, I promise you, E1 will actually multiply row 2 by 8, and E3 will multiply row 2 by 5, negative 5 actually, and add it to row 1. I promise that will be the case. I'm doing a video, I might as well do it, right? So let's do that one. E3 times A. Well, E3 was this. It was born out of multiplying row 2 by negative 5 and adding it to row 1. And then we apply that to the matrix A. And let's see what we get. The dot product of row 1 and column 1, that'll be 1 plus 10 plus 0, or in other words, 11. The dot product of row 1, column 2, well, that'll be 1 minus 5, which is a negative 4 plus 0. And finally, the dot product of row 1 and column 3, that'll be 1 plus 0 plus 0. Moving on to row 2. Well, interesting thing about row 2, you should probably know this by now. When you multiply it by column 1, it only keeps the middle element. So that's going to keep the negative 2. And then when I multiply it by column 2, it'll keep the middle 1 there. And then finally, multiplying by column 3, it'll keep the 0 only. Last row, again, we have a 1 only in the third position, everything else is 0, so it's going to zero out all my dot products except for their third entries. So if you look at column 1, column 2, and column 3, it's only going to keep the 0, 3, and 1. And if you look at this result, it looks very, very close to the matrix A, except that very first row. And that very first row is different because we have taken negative 5 times the second row and added it to the first. Negative 5 times negative 2 is 10, plus 1 is 11. Negative 5 times 1 is negative 5, plus 1 is negative 4, and negative 5 times 0 plus 1 is 1. 11, negative 4, 1. So there you go. You can see it actually does work out. All right, I think that's pretty good for this example. Let's move on. Well, here was my random next example, but we actually just did this, so I get to skip it. Yay for me. And here we arrive at what's going to be 3 theorems in a row. And to be honest with you, just to save time and my voice, I might not do every single proof here, just because I want to barrel through this stuff so I can move on with my day. This first theorem just says, if an elementary row operation is performed on a matrix A, and by the way, notice the size of that matrix. It does not have to be square. It can be an M by N matrix. The resulting matrix can be written as E times A, where E is an M by M. Remember, matrix products require their inner sizes to match. So that requires E to be the square M by M matrix. But remember, E is just derived from the identity matrix using a single row operation. So anyhow, the resulting matrix can be written as E times A, where the M by M matrix E is created by performing the same row operation on the identity matrix. I'm not proving that, mainly because we just showed some examples and I think it's fairly convincing that it does work. Now, if you want to see a proof of that, I would say you could probably, generally, I recall, these generally come in as homework problems. So this might be a homework problem that your instructor assigns. A very important thing I must mention before I leave this slide or this screen is that the product is always on the left-hand side. So the elementary matrix is to the left of A here. That's very, very important. Right side multiplication by the elementary matrix is not going to do what you think it's going to do. Going along with the theme of theorem after theorem after theorem, even though these are we kind of know these naturally, I think, each elementary matrix is invertible. Now, let me just stop there. Each elementary matrix is invertible. Now, why would I say that should be somewhat obvious? Well, I'll just go ahead and say because we've derived the elementary matrix from the identity matrix. And if you think about the identity matrix, it has a pivot in every column. While we don't have a theorem right now telling us having a pivot in every column is incredibly important for it to be invertible, the reality is it's true. If your matrix has a pivot in each column, and it's a square matrix, it's invertible. If we had that theorem, then I could easily just say this is trivial by that theorem, because E is row equivalent to the identity matrix. However, let's read the rest of this. The inverse of the elementary matrix is the same type that transforms the elementary matrix back into the identity matrix. That is, if your elementary matrix multiplied row 2 by 8, its inverse would divide row 2 by 8. That's it. That's all it would do. So it undoes what you do. That should make sense when you're talking about inverse operations. Again, this theorem is often given for homework as a proof, so I'm not going to do this as a proof here. And I promise this is the last theorem in this video, and then we'll do an example. But this is the last theorem we're going to have to deal with. And by the way, it's a super powerful theorem because this is basically saying what I just said a few moments ago. An n by n matrix A is invertible if and only if A is row equivalent to the identity matrix. And in this case, any sequence of elementary row operations that reduces your matrix to the identity matrix also transforms the identity matrix into A inverse. This is going to be the key to finding A inverse for large matrices. What this is saying is you start with some matrix A and you want to transform it into the identity matrix. Well, if A is invertible, that can be done. You apply one elementary matrix maybe to add one row to another, maybe another one to swap rows, another one to add a multiple of one row to another, and so on and so forth. And when you do all of those operations, if you do those same operations on the identity matrix, you should get to the inverse of A. Well, that's not actually the proof, but that is very close to the proof, believe it or not. So let's go ahead and start to outline the proof. And to do that, I'm going to keep it as general as possible. I'm still not going to do the full proof, but I know that if it can be done, we could take A and left multiply it by an elementary matrix, and we can keep doing that until we eventually arrive at, and I shouldn't use the subscript n there because A, I'm going to assume is an n by n matrix, so I'll use subscript k here. So we've applied k elementary row operations by multiplying by k elementary matrices, and all of those manipulations hopefully create the identity matrix. That is, A needs to be row equivalent to the identity matrix to have this conversation. But if A is row equivalent to the identity matrix, then we can apply the inverse of all this product to both sides of this equation. And remember, we have a theorem that says the inverse of a product of matrices is the product of their inverses in reverse order. And that actually holds for large multiplications. So if I multiply both sides by the inverse of this product right here, well, we know if, and this is a big old fat if, but if this product is well defined, then we can first of all regroup. And I'm not going to redraw this to regroup. I'm just saying group to where you have this inverse right here times this chunk of product right there. That inverse is actually the inverse of ek dot 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 to e2 to e1. So that highlighted bit is going to be the identity matrix. And it's going to equal that right-hand side times the identity matrix, but we know that matrix on the right-hand side times the identity matrix, well, it's just that ek to e2 to e1 inverse. That's it. Also, the identity matrix times A is just this guy right here. This tells us immediately A is invertible. So I've just assumed that we can multiply A by a bunch of elementary matrices to get to the identity matrix. If that's the case, then I arrive at the fact that A is the product of a bunch of matrices inverted. That is, A is invertible. There is some matrix that is A inverse, and that matrix is all of this stuff here. Thus, A inverse is actually the inverse, right? And we happen to have a theorem that says the inverse of the inverse is the regular old matrix. The inverses kind of cancel in a way. And so A inverse is E sub k dot 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 to E sub 2 times E sub 1. And you could throw on an identity matrix there if you want to. And that actually proves that if A is row equivalent to the identity matrix, then A is invertible. And that same sequence of elementary row operations that reduced A to the identity matrix also transforms the identity matrix into A inverse. Because here we are, we're transforming the identity matrix through the same row operations into the inverse of A. Now, I only proved it in one direction, but I feel pretty good about that. I'll leave the other direction to you, or to read in your textbook, because it technically probably is in your textbook, to be honest with you. And instead, I'm going to go into diving into an example. So here we have a big question. I want you to solve 3 different matrix equations, 3 different right-hand sides, but they all have the same coefficient matrix A. And that's critical here. So rather than doing row reduction 3 different times, I would love to be able to find A inverse, because if I could find A inverse, I would find the solutions to be x equals A inverse B for the very first equation, x equals A inverse C for the second equation, and x equals A inverse D for the final equation. If I happen to know that matrix A inverse, my life is very easy. Now, we are going to lean heavily upon Theorem 7, which told us that the elementary row operations, or the elementary matrices that we use to reduce A to the identity matrix, are going to be the same elementary matrices that we're going to multiply the identity matrix by to get A inverse. And to do this, I'm going to introduce an algorithmic method for doing this. So every time that you perform an elementary row operation on A, you want to perform that same elementary row operation on the identity matrix. If you do that, you'll slowly build the inverse, A inverse. So through a bunch of elementary row operations, you should end up with a system or an augmented matrix like this. Now, I should mention something about this augmented matrix. The left-hand side is, in our case, a 3x3 matrix. And so the right-hand side of that bar is also a 3x3 matrix. It's the identity matrix. And we'll use the same row operations throughout on all rows and all elements in this. So let's see this via example. So here we have it, the matrix A augmented with the identity matrix I. And I'm going to start multiplying the matrix A by elementary matrices. That is, I'm going to perform elementary row operations. Those same elementary row operations, if I perform them on the identity matrix, I'll slowly build A inverse according to Theorem 7. So I am going to do my elementary row operations kind of quickly here. Now I'm going to pause right here because I want you to notice on this first move, what I've done here is I've killed off everything below this pivot. So I've made everything below that pivot 0. However, also notice that simultaneously in the identity matrix part, I am making all the elements below it non-zero. So kind of undoing things in the background. Let's continue forward. And you see an issue where we start getting fractions involved. And generally I try to tell students, avoid fractions till the very end. But in this case, this -8 and that -7, they're just not going to kill each other off easily without introducing some fractions. So I just decided to do it. You don't have to. You could have left that as a -8 in this pivot right here, and then just said, well, I'm going to take -7/8 times row 2 and add it to row 3. And that would keep fractions out of that second row, but it would still give you fractions in the third row. So I just decided to go ahead and just do it. Now that we're down to here, I'll go ahead and divide that bottom row by a -4. And you can see the mechanics of this can be really daunting. A lot of arithmetic can happen in here, a lot of arithmetic mistakes, that is, can happen in here. So you do have to be very, very careful. I'll go ahead and start the backward phase using this pivot right here. And finally, using this pivot right here, we'll go ahead and finish the process. Okay, so that looks like a pretty daunting process. I would say that it is, but it's only worthwhile, to be very honest with you, if you have multiple equations with the same coefficient matrix, but just different right-hand sides. And that's what we're going to use here, because we were given ax equals b, ax equals c, ax equals d, And we've just found A inverse, so all I need to do is take that inverse matrix and multiply it against B, C, and D. That part is actually the fast part. You get faster finding inverses, but it takes a while to get there, to get proficient enough to do it, and there are better algorithms that are in existence. But let's go ahead and do that. The way I'm going to do this is I'm going to steal this right now and rewrite it up above where I don't have so many fractions in there. What I'm going to do is divide out 1/32. And there we have it. Let's go ahead and use that A inverse and multiply it against B, C, and D to find out what the solutions to those equations are. And I should probably label these values something other than X, X, and X. It should be X, Y, and Z or something like that. Well, let's figure this out. X is equal to A inverse times B. Computing this product out, we get to here, and that is obviously 1, 1, 1. Doing the next one, this is A inverse C. That's what Y is equal to. So doing this multiplication, we get that Y is the vector 1, 0, 1. And finally, working with Z here, Z is A inverse D. Doing that multiplication, which is negative 1, 1, 0. So you could see in this instance here, actually most instances, honestly, that if you find the inverse, well, if you're going to want to find the inverse, it's only because you're really dealing with multiple equations having the same coefficient matrix. There's just no way around it. It's more efficient to find the inverse matrix than doing row reduction techniques over and over and over again for those. However, you could see that finding the inverse can be pretty darn messy. But we did it here, and I hope that you didn't find it too painful, at least the process of going through the arithmetic. Be aware you're going to make arithmetic mistakes, so keep on top of that. And I hope to see you in future videos. I hope this was helpful. Have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to